Hey, fellow mathers! Welcome to the podcast where math is figure-outable. I'm Pam Harris, a former mimicker turned mather.
And I'm Kim Montague, a reasoner who now knows how to share her thinking with others. At Math is Figure-Outable, we are on a mission to improve math teaching.
We know that algorithms are amazing historic achievements, but they are not good teaching tools because mimicking step-by-step procedures can actually trap students into using less sophisticated reasoning than the problems are intended to develop.
In this podcast, we help you teach mathing, building relationships with your students, and grappling with mathematical relationships.
We invite you to join us to make math more figure-outable. All right, that's getting down. I'm getting that down. That sentence is so long.
Well, you've said that. You can do something about it.
No, but it's such a good one. Like, I've had several people tell me that they really like it.
Yeah.
So I just take a deep breath and it's like my days of playing the trombone. It's like
you played the trombone?
I did. Do you want to know why? Because I wanted to be in the. She's like, no, but I'm saying anyway. I wanted to be in the band, and I told my parents I wanted to play the drums. I was like all over. My dad played the drums. I was like, I want to play the drums, and they were like, okay, you can be in the band. And my dad came home one day, and he had this beat up old trombone, and he goes, hey, check it out. I've got an instrument for you. And I was like, I'm sorry, what? I want to play the drums. And he's like, yeah, but I was able to get this free trombone. I was like,
that is not the drums.
So not. They said, play it for a year and then you can play the drums and whatever. Anyway, I played it for like 4 years. It was fine.
That's amazing. How do I not know that? It's always fun when after 2 years, something new. Okay.
The good part about playing the trombone is I was the only girl always. And
yeah,
so
of course.
It was like me and the guys.
I shouldn't say of course. Yeah. Lots of trombone players are women.
I'm sure there are.
Not in a band I was in.
Not in mine. And it was great. The ratio was in my favor. I had a blast being
Excellent.
the girl trombone player. Okay. All right, Kim, let's do math.
Yeah. Well, but first,
okay.
We have this lovely, lovely woman named Kim.
Oh,
hi, Kim.
We like people named Kim.
Kim Bright. She left us a review. It's been a while now, and I've been saving it because
is that good?
Well, it's fun. She says my favorite math podcast.
Aw, thanks, Kim.
I love listening to Pam and Kim share different ways to think about teaching math. I've gained so much from them, and implement a ton of what they're sharing into my teaching practice. They are fun to listen to and break down math in real, fun, and practical ways. Thank you for sending the message that the use of reasoning and understanding of numeracy is the way to understand math. I'm here for it, and so are my students.
That's
We're
awesome.
here for it too, Kim. Thanks.
Thanks for the 5 stars, Kim.
Yeah.
And listeners, thank you so much for giving us reviews and what do you call that? The rating, right? Rating?
Yeah.
Rating and reviews. The algorithms for podcasts, if we get the more ratings and reviews we get, then the more listeners can find the podcast and the more we can help revolutionize the way we teach math. So we appreciate you guys helping us get the word out.
Okay. So the last couple of weeks, we've been talking about fractions, fraction multiplication, and we did an episode on unit fractions and unit fraction by a unit fraction.
Mm-hmm.
And then last week we talked about taking that understanding and using scaling to think about non-unit fraction multiplication.
Yes.
So
nice.
Today let's go some more.
Yeah. So if you have not listened to those, we are really not going to recap a lot of that. So we're going to build off of it. So you might want to listen. I mean, you're welcome to listen to today, but as soon as you hit something, you're like, what? Then it might be because maybe we're building off of we are, not maybe, but yeah, check out the last 2 if you haven't heard them yet. All right, cool.
Mm-hmm.
So Kim, I'm going to throw out a question and I just want to hear your thinking. Don't try to give me what you think I want. Just tell me actually how you think about it.
Okay. Do I ever?
I mean, pretty much. Yeah. So Kim, if I were to say 2/5 times 3/4, 2/5 times 3/4, what do you get?
Yeah. So I think I mentioned this last week that when I think about a fraction times fraction multiplication, then I think about, I'm actually going to write down what I think in my head. So I actually think 2 times 1/5 times 3 times 1/4. So I think about the 5th and the 4th and as the 20th, but then I scale up like we talked about last week times 2 and then scale that up again times 3. And so for that, I get 6/20.
Cool. And then you would probably also think about simplifying that 6/20. Just,
I mean, if I had to, if somebody said
if you had to, but you wouldn't have to. You could think about that as 6/20.
Yeah.
Cool. So that would definitely be a way that you could think about that. if you weren't thinking about the last 2 weeks, I wonder if there's any other way you might think about 2/5 times 3/4.
I mean, do
Like,
I get to play?
yeah, you get to play.
Okay. Okay.
Play a little bit.
Okay. So if I was thinking about 2/5 times 3/4, then I would actually think about 3/5 times 2/4. And that would be half of 3/5.
Because 2/4 is 1/2.
Yeah.
Okay.
So half of 3/5 is 3/10.
How do you know half of 3/5 is 3/10?
Because if I think about 1/5 and I think about half of that, half of 1/5 is 1/10.
Mm-hmm.
So half of 3/5 is 3/10.
Nice. Um, any percents coming to mind just while we're playing a little?
Well, yeah, I mean, I think 50% of 3/5. You could also think about 40% of 75 or 75% of 40. Like, I mean, it's just a
If
good
you go
problem.
if you go back to the original problem, 2/5
Yeah.
times 3/4. You're saying you could think 2/5 is 40%?
Or even more fun would be 75% of 0.4.
So slow that down just a little bit, because
Okay.
the problem is 2/5 times 3/4, but you're thinking you could think about 3/4 times 2/5
Yes.
as 75% of
0.4.
2/5, which is 0.4.
Yeah.
Why would you think about 75% of 0.4? I love it. I love it. I love it. I love it.
Because uh 75% of point
You're like, how do I verbalize this?
75
3/4? How about three
three
fourths
fourths
of
of
40?
40 cents is
Yeah,
30 cents.
30 cents. Bam, and there's your 3/10 again.
Yeah. This would be a
Yeah.
great math strat chat problem once you do a lot of work with your kids and
Because
relationships. There's so many fun things on this problem. I love this problem.
so many things you could do with it. Yeah.
Yeah.
Cool. Okay. So now that we've established that 2/5 times 3/4 is 6/20 or 3/10, which is equivalent to 3/10.
Mm-hmm.
Another way that we could also model that would be kind of based on a little bit about what you said earlier. I'm going to draw a candy bar. And so I've got a rectangle, kind of a horizontally a little bit longer rectangle. And I'm going to think about 2/5 of 3/4 by thinking about a fifth of a fourth first.
Mm-hmm.
So I'm thinking about fourths. I'm going to cut the whole candy bar vertically into fourths. And then I'm going to cut the whole candy bar horizontally into fifths. Okay, so now I've got sort of a 5x4
Mm-hmm.
to represent fifths by fourths. And if I think about a fifth of a fourth, that's kind of that upper left-hand rectangle. But we needed 2 1/5, so I double that. So now I've got 2 of those fifths in that left-hand column. And then we need 3 1/4, so I'm going to triple that across. And so my rectangle now looks like kind of a 5x4. Do I hear your pencil? I think I hear your pencil.
Sorry.
No,
I'm
that's
sketching
awesome.
your picture.
You pencil person, you. And then, so where did I even say? I've got like a 5x4 where I've got the 2, how do I say this? A 2x3 shaded in the middle of it. Does that track for you?
Yeah. So your
2 by
big
3?
rectangle, your outside big is a 5x4.
Mm-hmm.
And then inside of that, you have a 2x3 shaded.
Yes.
Okay, cool.
And so that's kind of those 6/20ths. And like we talked about last time, I could count each of them. I could look at those 6 as 3 2-chunkers. And that would be 3 2-chunkers out of the 10 2-chunkers. That'd be another way to see the 3/10. That we're not going to go there today. So focusing on that, the 6/20ths, I've got sort of 6 out of the 20 shaded.
Mm-hmm.
Okay, cool. Next problem. What is 3/5 times 2/4? And I think you even did that when I asked you to think about
well,
the other one.
you let me play with a bunch of things.
I did let you play. What is 3/5 of 2/4? Say it again.
That is also 6/20ths or 3/10.
And that's because you thought about 2/4 as 1/2. And that's when you did the whole half of 3. Yeah, anyway. So okay, so you're saying they have the same answer, right?
I do. Mm-hmm.
Okay, so 3/10 or 6/20. But I'm going to go ahead and represent a rectangle that is 3/5 by 2/4.
Okay.
So underneath the rectangle for the first problem, I'm drawing the same rectangle, but this time so like the outside is the same, but now I'm going to draw, I can think here. I'm going to still do fourths vertically and still do fifths horizontally. That takes me a second. Okay. And now I'm going to do 3. So I've got a fourth of a fifth is that top left-hand rectangle. And I've got 3 of those 3. I'm going to scale that times 3. That little guy times 3. So now it's down there times 3. So in that left-hand column, I've got 3 rectangles shaded in. But now it's 2/4. So I'm going to double that.
Mm-hmm.
And so now my rectangle looks like a 5x4, but the inner shaded rectangle is a 3x2.
Mm-hmm.
Does that track?
Yep.
Okay. So if I was doing this with real kids, because you're not a real kid,
Sometimes.
then I would have the problem 2/5 times 3/4 with the one rectangle, and the problem 3/5 times 2/4 with the other rectangle that we've just described.
Mm-hmm.
And then I would step back and I would say, what do you see?
Mm-hmm.
So, Kim, if you were a kid or yourself, what are some things you might see?
So in the first problem, I have numbers all over the place. I
Mm.
think the first problem was 2/5 times 3/4.
Mm-hmm. Mm-hmm.
Okay. So in the original first problem, I still am thinking about fifths times fourths,
Mm-hmm.
but I only had 2 of the fifths and I had 3 of the fourths.
Mm-hmm.
But this time I'm still thinking about fifths times fourths, but I have 3 of the fifths and 2 of the fourths.
Mm-hmm.
So you can see that in the representation that you sketched because the 2 and the 3 are reversed, they're swapped. And it looks like a rotation in your model.
The shaded part, right? Because the outside rectangle looks the same. It's still 5x4.
Mm-hmm.
And the inside shaded guy went from a 2x3, rotate to a 3x2.
Mm-hmm.
But like you said, both of them are thinking about a fifth times a fourth and then scaling either times 2 times 3
Mm-hmm.
or in the second one times 3 times 2.
Mm-hmm.
So we end up with 6 shaded pieces out of the 20 shaded pieces. It's just they're sort of rotated a little bit.
Mm-hmm.
And that can be a spatial way to help kids sort of think about the commutative property in fraction multiplication. That they can literally reason through a problem like 2/5 times 3/4, but they could also say to themselves, yeah, but I could rotate that inner array. Thank you, Kathy Fosno, by the way. So I learned this rotating the inner array from Kathy Fosno. I probably should have mentioned at the beginning, maybe. Golly, is that in Parks and Playgrounds? So she has a wonderful
Yeah.
unit out there. I think it's called Parks and Playgrounds, Measuring Parks and Playgrounds, something about Parks and Playgrounds, where it's this idea that you can look at the shaded inner array and you can watch it rotate, and that kids can go, oh yeah, multiplication is commutative. So I think there's 2 things happening here. One, we have a spatial justification for the idea that the numerators can kind of switch places, or that you use the commutative property. But also there's kind of, Kim, your scaling idea going on. When you talked about 2/5 times 3/4, you said that you were thinking about that as 2 1/5 times 3 1/4. And so once you can kind of think about that 1/5 times 1/4, like the way I have it written down on my paper is 2 parentheses 1/5 times 3 parentheses 1/4. I can
Yep.
use the commutative property right there
Yep.
and think about 1/5 times 1/4. That's the 1/20th. And then think about that 2 times 3 as the 6.
Yeah.
So what that means is we can have other problems where once we realize that we can make those fractions into the numerator times that unit fraction and the other numerator times its unit fraction, then we can kind of go wild with the commutative property, and out comes this idea of simplifying either first or at the end, because really we kind of use the commutative property to do it. So for example, I could give you a problem like 2/5 times 5/6.
Mm-hmm.
And you could at that point decide, well, let me back up. The way that I've seen a lot of teachers handle this is they go, okay, either multiply straight across. Now kids are rote memorizing a rule and they're mimicking it,
Yep.
and then they have to remember which rule to do when.
Yep.
Or the teacher says, no, we're going to get some modeling out of this. And so they say, draw a rectangle, cut one side into fifths, shade 2 of them, cut the other side into 6, shade 5 of them, count the double shaded pieces, count the total, and then represent the shaded pieces out of the total. We're submitting that that's another procedure that kids are rote memorizing and mimicking, and then they're stuck in counting strategies because they're counting what's coming out of it. So we're not recommending either of those when a kid hits 2/5 times 5/6. But we're also not recommending that teachers start to slash and burn at this point. Where they're like, okay, so I can see 2/5 and 5/6. Hey, those fives are the same. I'm just going to like cross them out and pretend they don't
the
exist.
same.
Yeah.
The same.
Right. And so now we've got this sort of slash and burn thing happening, and they're cross canceling or whatever, all these things that then kids start to cross cancel no matter what is happening in between the fractions.
Right.
So we're also not suggesting that that is the first go-to. How could kids look at a problem like 2/5 times 5/6 and use reasoning to go from there? Kim, I'm not going to say much more than that. What are you thinking about?
So I thought 2/5 means 2 times 1/5. And I wrote 2 times 1/5. And then I also wrote times 5 times 1/6. So on my paper, I have 2 times 1/5 times 5 times 1/6. That's what that fraction multiplication means. So within that, I have 1/5 times 5, which means like it's equivalent to 1.
And we would want kids to know that, right?
Right.
Like that's not a, oh, look, there's a 5 in the numerator and a 5 in the denominator. We can slash and burn them. No, we want them to actually think about what 5/1/5 means.
Yeah.
That's an important understanding.
Yeah.
5/1/5. Cool. So now
then I have 2 times 1/6
left over.
Means, 2/6 is a third.
And 2/6 is equivalent to 1/3. Cool. And how are you thinking about 2/6 being equivalent to 1/3? And I know you're probably not thinking about that very much, but if you had to think about it.
I don't know.
You've got that one pretty ingrained.
I
right?
mean, yeah.
I wonder if you were to think about your 2/1/6. Does that, I don't know, does that do anything?
I mean, if I thought something was, cut into 6 pieces and I had 2 of them, then it would be equivalent to if I had that same thing cut into thirds.
Yeah.
Yeah.
That's one way to think of it. Sure. Yeah. Nice. So, Kim.
Yeah.
We actually want kids to think about fraction problems where it's not just slashing and burning, but they're actually thinking about unit fractions, the numerator times unit fractions, scaling times unit fractions, so that they can make sense of the fact that they're using the commutative property, and then they're going to end up with things like 5 times 1/5 and 2 times 1/6, and that they can make sense of what those things mean. Instead of just mimicking an area model. Go ahead.
Yeah. Well, and I was going to say, when you give kids the opportunities to have some real understanding, that is one way that they could think about that problem. But there's several other ways. And I think that's what we're looking for in a classroom, right? That not we wouldn't want an environment where every single kid in the classroom does what I just said to solve 2/5 times 5/6, because it's a rich problem where we should have a variety of strategies. And we only talked about one. I don't know if we want to talk about some other ways to solve that problem, but if we built on unit fraction, we talked about scaling, we just did this kind of commutative property, swap the numerators thing. But also we could have kids that say, well, I know 1/5 of 5/6. So I could double it to get 2/5 of 5/6.
What is 1/5 of 5/6?
1/5 of 5/6. So 1/5 of 5 is 1. So 1/5 of 5/6 is 1/6.
Nice. But we need 2/5.
So it's 2/6.
So you're going to double that to get 2/6. I love it. You got any more? Put you on the spot.
So 2/5 of 5 is 2. So 2/5 of 5/6 is 2/6.
Nice. Well done. Yes.
Well, I was going to say, and that's, I think that's what we're hoping for in a classroom, that we don't just say, let's have meaning and all still do one way to solve a problem. It's about building kids' brains so that they can look at the numbers and see what they're playing with in that moment. Oh, this reminds me, we had somebody in one of our Facebook groups. We have a couple of different groups that we run, And one of the people said, hey, I have this question about my son, and he used to think about this multiplication fact this way, but lately I've noticed he's been thinking about it this way. Is that okay? And I said, that's absolutely brilliant. That he used to, the last time she asked him how he thought about, I don't know, maybe it was 8 times 4, he was thinking about it like 4 times 4 doubled. But now he's thinking about it like 10 times 4 back 2 times 4. And she was like, is that okay? And I was like, yes, that's desirable. Yay, go him.
Yeah, we actually want multiple connections in kids' heads, right? We want multiple ways, that multiple paths, multiple representations. We want, it's not about, this is a high school thing. A lot of high school teachers will say multiple representations. And I'm like, it's not about multiple representations. It's about the connections between multiple representations. We want to have a web-like series of connections in kids' heads so that they can use the one today that flows the easiest, but also the one tomorrow that's going to connect to a different problem. Kim, I was just having a conversation yesterday with a mathematician at church. This guy, he makes me think, oh my gosh, every time we talk, I walk away going, let me think about that for a half an hour.
That's awesome.
So amazing. And his new project is he's working on new encryption algorithm. Not encryption. He used to do encryption. Now he's doing, oh golly, what do you call it when you make files smaller? Not condensing, but oh my gosh, my brain. When you
no idea.
Yeah, when you like take something and you make it into a zip file so that it compress. When you compress files, okay, people are yelling at their yes, compress files. I know. Anyway, so he's working on compression algorithms, and he was saying, hey, a lot of compression algorithms out there only work for certain kinds of files. And when you compress, it's pretty good if you can get like a 70% compression ratio. So that, if it was this big, now it's only 30% as big as it was. Then that's really good if you can compress it that much. But he's working on a compression algorithm that you can iteratively compress. So you compress it, and then you can compress that one, and then you can compress that one. And we were starting to talk about, I kind of get a lot of what he was talking about, but I don't get how you uncompress. Like, how do you not lose data when you, anyway, blah, 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 blah. What we were talking about was, he said, yeah, it's super important that people, he can't find people to work with because he said people don't understand topology and number theory enough. And I said, hey, Al, I'm super curious. When you say that, would you agree with me that it's a big reason in a big way, people don't understand number theory? Because when they were actually doing numbers, they were taught to mimic and memorize and mimic algorithms. And he goes, yes, all they did was mimic and memorize algorithms. And so now that when they get to me, they never reasoned through the numbers. And so their number theory is poor. And then add on to that, they haven't had enough topology and they can't put those together. The reason I'm mentioning this whole story is his brilliance in mathematics, like he is published a lot, is that he brings together these sort of disparate areas of mathematics. Like one of the reasons he could do what he does is because he brings together topology with things like set theory, with things like number theory, and his unique way of bringing those connections together is where he adds to mathematics. I know I just got all excited about it, but that comes to mind because when you're mentioning this kid solving a problem in two different ways, it's about connecting. It's about connecting different ways of thinking. That's mathing. That's what mathematicians do. Now, Al, my friend, does that with higher math, but we can do that very kind of thing with today. Today, we did it with fraction multiplication. Bam!
Yeah. And it's why it's so important that we give kids so many experiences and bring all this stuff together, because when they understand what a unit fraction is and how to operate on it, and they own the commutative property and the relationships between decimals and fractions and percents, they have choice and they have really cool strategies at their fingertips.
They have options. More importantly, they've built reasoning and they are mathing.
Yeah. Thanks for listening, everyone, and for leaving us a review and for sharing the Math is Figure Outable movement alongside of us. We love doing this, and we want as many people to know that we are so grateful for you and this movement. Keep spreading the word.
Bam! Thanks for tuning in and teaching more and more real math. To find out more about the Math is Figure Outable movement, visit mathisfigureoutable.com. And keep spreading the word that math is figure outable.